Hello, everyone. Thank you so much for being here today. We will be discussing mathematical phenomena, testing the limits of theory. My name is Rameen Iftikhar. So, I'd like to start off by introducing myself. My name is Rameen Iftikhar. I am an A level student. I am originally Pakistani, but I was born and raised in the UAE. I am currently studying to hopefully be a data analyst. I really like the field of tech and all of that stuff. And my interests are mathematics, AI, and music. Mathematics, as you guys can probably already tell. And I'm very honored to be presenting this. It's a privilege to get to talk about something that I'm really interested in. And I hope that you guys enjoyed the session and enjoy learning about this stuff as much as I do. My hobbies, sports, art, mentoring. With mentoring, I feel like I really love learning new stuff, researching, and I love sharing my knowledge with others, which is, of course, why I'm very excited to be able to speak here and to be able to, hopefully pass on my knowledge and to be able to hopefully make you guys as interested in this subject and everything that we're talking about as I am. I am the moderator for STEM Quest 3.0, so you guys might have heard my name. So I am super excited. And without any further ado, let us start. So, the things we'll be talking about in this session, we will first off start off with an introduction. We will be discussing four main topics, phenomena, where the first one will be the bell curve, the second will be the gambler's fallacy, the two envelopes problem, and my personal favorite, Hilbert's Hotel. And after that, we will be discussing the takeaway from what we learned from all of these phenomena and summarizing everything up and answering the question, where is the limit of mathematical theory? And then you guys can ask me any questions that you have. I'll be more than happy to answer them regarding any of the phenomena that we have discussed. And yeah, that will pretty much be it. So let us start with the introduction. Mathematics is all around us, yet we never really notice it. Now, I feel like as a part of STEM Quest, or even as a part of STEM, mathematics is kind of disregarded or put to the side. I mean, let's be honest, when you think of STEM, the first thing you probably think of is science or technology. I feel like the last thing we kind of really think about is mathematics, and we haven't really had that many sessions on mathematics. So it's really refreshing to be able to end off STEM Quest talking about mathematics, especially considering that all of the STEM concepts, science and technology, they are built on the backbone of mathematics. Mathematics is the fundamental element behind all of STEM. So I'm really excited to be able to talk about that. You are using math every day, constantly but subconsciously. Our brains are constantly calculating, comparing, and predicting. Predicting whether you can cross the road in time, calculating and splitting bills among your friends, and so, so much more. Everything around you uses mathematics. You are using mathematics every day, but it's become such a regular part of your life that you don't really notice it. You don't think twice before anything that you do. Let's say you have to get somewhere and you have to walk straight and left. Now, you wouldn't want to walk straight and left. You would want to walk diagonally so it saves you more time. That is math. That is the Pythagorean theorem. But you don't really think of it as the Pythagorean theorem. You are so used to math being a part of your everyday life that you disregard it and you don't really think twice before you do any of this. Let's say you're at a restaurant with two of your friends. The bill comes out to be $60. And without thinking twice, all three of you pull out a $20 note. So that is that is how we can kind of, say that math is a part of our everyday lives, but we don't notice it. We Math is everywhere, literally everywhere. From the moment you wake up, and it's not just you, it's everything that's around you. From the moment you wake up, your alarm clock rings. Your alarm clock is on your phone. Your phone runs on a series of zeros and ones. Your phone is running on algorithms. There are millions of algorithms that are, you know, being processed every single second. But that is that is kind of that is what's behind all of this. Everything, every device that you have runs on zeros and ones. And basically, all of STEM points back to mathematics. But why should we test mathematical theory? Now, I find this very interesting, but let me let me kind of say this. Mathematics assumes perfection, and reality, of course, adds limits. And we know that there's a huge gap between the both. Now, let me give you guys an example. If I mean, I am assuming a lot of you guys are in high school or have been in high school at some point. And if you've ever had a lab lesson, your teacher might have asked you to write a hypothesis. If you're performing an experiment, your teacher has probably asked you to write a hypothesis before you perform the experiment. Your hypothesis is what you believe is going to happen once you perform the experiment. Your hypothesis is what you're expecting, but your hypothesis doesn't always have to be right. It can be, there are no right answers to a hypothesis. That is just what you believe will happen. Now, let me give you an example. For example, you are performing an experiment and you are expecting 500 joules of energy to be emitted. But once you actually perform the experiment, let's say only 480 joules of energy is emitted. The rest of the energy might have been lost to the surroundings or might have been lost as thermal energy. But that is kind of how we can explain that the real life has constraints. The the kind of situation, the situation that we are performing the experiment in, these are not the perfectly ideal conditions. We can never have perfectly ideal conditions to perform an experiment. Sorry. So that is kind of where we say that reality adds limits. We can't we can't always, translate everything into the real world. So we know that mathematics in theory, of course, is perfect, but can it always be applied in real life? What do I mean by this? Let me take a, let's say infinity. There are certain concepts in mathematics that cannot exist in the real world. For example, if I were to give you a number line and I were to tell you to plot infinity on that number line, you of course would not be able to do that. Or if I were to tell you to give me an infinite amount of products, you would not be able to do that because infinity is just a concept. It cannot be present or it cannot be applied in the real life. Same with imaginary numbers. If I were to tell you to give me four apples, you would look at me like I'm crazy because imaginary numbers do not exist. These are just concepts that are a part of math that cannot directly be mapped onto the real world. So let me ask you this. Where is the limit of theory? Now, this is basically what we will be discussing throughout our whole presentation. So I'm really excited for that. So let's move on to our next phenomena or concept, the bell curve. Now, with a show of hands, can I know how many of you have seen this shape? All right, so it looks like a few of you have seen this shape. Perfect. This is called the bell curve. Now, let me tell you a very interesting fact. If you were to take the heights of all the adults in a country, you would end up with this shape, the bell curve, or which is also called the normal distribution curve. Same with height or weight or IQ or literally anything. Why does this happen? This is due to the central limit theorem. This is a theorem in mathematics, which is which states that the distribution of sample means will become approximately normal, which is the distribution. This is the normal distribution, bell shaped as the sample size gets larger, regardless of the original population's distribution. So, if you have a very large sample size and you plot that onto a graph, you will almost always end up with this shape, the bell curve. Now, if I were to take the height of all of my classmates, 30 students, for example, and if I were to plot that on a graph, that would probably not look like a bell curve. Why? Because the sample size is too small. It's not as large as the bell curve. It's not, sorry, it's not as large as the sample size that would be required when we need to see the bell curve. So Most people are average. Think of yourself and your life. You may not notice it, but the bell curve appears almost everywhere you go. In a classroom, there are very few people that get an F. There are very few people that get an A star, but most people get B's, C's, or A's, which is the average. Most people are average, which is why average is called average. But why does any of this matter? Why are we talking about this? And how do mathematicians use this bell curve to, how do they apply it in real life? So the bell curve helps us predict outcomes. Casinos, sports analysts, and even Spotify recommendations rely on bell curve distributions. Let us take Spotify for example. Most users prefer songs similar to what they already listen to, which places them near the center of the distribution. Spotify predicts this by recommending music close to a user's average taste, since extreme preferences are statistically less likely. So let's say you are the user and you are listening to pop music, and you're listening to a lot of pop music, which will place it around here. Now, Spotify will try to recommend you music closer to your average taste. So when Spotify is recommending you something, a song, it will probably recommend you something that's right here and not right here. So if this is pop, let's say this is pop rock or indie pop, Spotify will most likely recommend you what's over here, not here. Let's say this is country music. A person that listens to pop music will more likely want to listen to pop rock music rather than country music. So Spotify recommends you what's closest to what you already listen to, because it is very less likely that someone that listens to what's over here will want to listen to what's over here. So by understanding what's most common, it helps us predict what's most likely. Now, this isn't, of course, always applicable. There can be some people that enjoy pop music as well as country music. But the majority of people that do prefer pop music also prefer indie pop or pop rock more than they prefer country. So that is why Spotify recommends the songs that the way that it does. I find this really interesting actually. So the bell curve essentially helps us turn patterns into predictions, but it doesn't predict what's going to happen. It predicts what's most likely to happen. That is a really common misconception. Moving on to our next phenomena, the gambler's fallacy. Now, after I explain this, you guys are probably going to be like, this kind of seems like common sense, but in the real life, we face this everywhere we go, and I will give you guys examples on this. Now, let me ask you a question. If something hasn't happened in a long time, is it more likely to happen next? Let me rephrase this. All right. You flip a coin and you land heads 5 times in a row. Before flipping it again, you think tails is due, except it isn't. Your intuition is sort of lying to you. Let's take other examples, more common examples, MCQ tests. During an MCQ test, you pick B 3 times in a row. And when the next answer seems to be a B, you doubt yourself. And this has happened to me so many times. And I believe this has also happened to you guys so many times. And this is a subconscious decision that our brain is taking. We don't really realize it, but that's just how our brain works. Or another example, a family has 3 boys in a row. At the gender reveal, the people say, next one has to be a girl. But that is not really, that is so mathematically wrong. Assumptions like these seem logical, but they are very, very wrong because mathematically, there's still a 50-50 chance of either. When you flip a coin, you either get heads or you get tails. Whatever results you got before you flip the coin does not relate to what's going to happen next. So, why do our brains think that way? That is what we call the gambler's fallacy. The belief that random events correct themselves over time. We expect outcomes to balance out, while in reality, balance only appears over very large numbers. Balance only appears over very large numbers, as we had just discussed with the bell curve. Patterns and predictions and being able to predict what's going to happen next, or being able to work out patterns from a set of data, only really appears over very large numbers, as we discussed in the bell curve or any other distribution that we have. That is how that works. But our brain sort of tricks us. But at the end of the day, there really is a fixed probability. The universe does not keep score. If you get a result many times in a row, that doesn't mean that the next, getting the same result another time in a row, it becomes less likely. The chances are still the exact same. That's just what the human brain thinks. That belief that random events correct themselves over time. But none of this really, anything that happened before the event doesn't really affect the event in a way. So randomness has no memory and the universe does not keep score. I find this quite interesting actually because a lot of times, we're just, even if we're thinking about the fact that there's still an equal chance of either of it happening, we subconsciously think that way. And there is kind of no way to stop it, but we can realize that our intuition is lying to us. Now, moving on to two envelopes. Now, this one's a really interesting one. So, and it includes a bit of math. So, I want you guys to listen up. Imagine you are given two envelopes. One contains a certain amount of money, and the other contains double the amount of money of the first envelope. So, you have two envelopes. Now, you pick an envelope, and let's model this by representing the amount of money in your envelope as X. So, we know that one contains a certain amount of money, and the other contains double. Since your envelope is X, this means the other must contain either 2X or X over 2. This is what we assume, since one of them has double the amount of money. So if we picked one, the other could be either 2X or X over 2. Right. So since there are two envelopes, let us assume equal probability. There are only two options. So there must be a 50% chance that we have 2X in the other envelope and a 50% chance that we have X over 2 in the other envelope. You are now given the choice to either keep your envelope, keep this one, or to switch it with what's in here. Except you don't know if this envelope contains 2X amount of money or X over 2. Let's calculate the expected value of switching. You have this envelope and you're trying to calculate the expected value of if you receive this envelope and whether it will be 2X or X over 2. So we know that there's a 50% chance that it's 2X and a 50% chance that it's X over 2. Let's calculate the expected value of switching. Since there's a 50% chance of it being 2X, so that's one possibility, and that's the other possibility. How do we calculate this? 0.5 multiplied by 2X, that's one possibility, and X over 2 multiplied by 0.5, that's the other possibility. And we add those two together, and that is our expected value of switching. That is how we calculate the expected value. If we work this out, this comes out to be X and this comes out to be X over 4. And that comes out to be 1.25X. And we know that 1.25X is greater than X, so mathematically, it seems better to switch. But let's say we switch, all right? And now you have the other envelope. If you apply the same reasoning and logic to this envelope, math tells you to switch it again because the other envelope now has a 1.25x chance of it being 2x. So mathematically, we are told to repeat this. If we repeat this process and repeat this logic and this reasoning over and over again, mathematics tells you to keep switching. Now, this seems to be the situation seems to be based on the conflict between infinite expectation versus finite reality. Infinite expectation being mathematics telling you to keep switching, which obviously you can't do, versus finite reality. But mathematics is always theoretically correct. We know that. So where does the problem occur? How come mathematics gives us a solution that is impossible to implement? This paradox is built on a false assumption, which makes the 1.25x calculation mathematically false. Now, I'd like to give you guys a chance to answer. What do you guys think is the false assumption that leads us to this value, which is wrong? What what makes this paradox a falsidical paradox? What assumption makes it that way? If you guys have any answers, you can turn your mic on and answer. All right. If there are no guesses, let me tell you guys. The flaw that causes this paradox is the assumption that the x values are a fixed that the value of x is a fixed amount, when in reality x depends on the envelope that you pick. Let's say this envelope contains $10 and this one contains 20. Now if you pick the envelope with $10, the possibilities are either 20 or 5. But if you pick the envelope with $20, the possibilities are either 10 or 40. So x is not a fixed amount as such. So us assuming that x is a fixed amount is where this phenomena went wrong and is what caused this paradox. This flawed assumption is what classifies this paradox as a falsidical paradox. So this paradox is sort of built on the backbone of a false mathematics assumption. If you guys want to learn more about this, I have my contacts at the end, so you guys can talk to me about this because I find this really interesting. And if you have any more questions, you can ask me in the end. And especially falsidical paradoxes are such an interesting concept to me because this is what kind of there's a line between paradoxes that are actually due to math. And of course math is never inconsistent, math is always logically correct, but a flawed assumption is what causes a falsidical paradox. So, and there are many different examples of falsidical paradoxes such as these, and they're very interesting. So if you guys do want to learn about that, I would recommend it a lot because I am looking to hopefully do that as well. So that was pretty much it. So we can conclude the two envelopes paradox as a falsidical paradox. So moving on to Hilbert's hotel. Now this is my favorite out of all of them. I find this really interesting. Now, let us say we have an we have a hotel with an infinite amount of rooms that is fully occupied. All right. So we have a hotel, infinite amount of rooms, and infinite amount of guests. That's our hotel with infinite amount of rooms, and it is occupied. So there is an infinite amount of guests. Now, a new guest arrives, and the hotel is supposedly full, right? We have an infinite amount of rooms and an infinite amount of guests. But can we accommodate the guest? You are the manager, and you think for a while, and you come up with a idea. You come up with an idea. You get on the PA, and let's say each person's room is N. So the blue guy is in room N, which is one. The pink guy is in room N2, and then so on. You get on the PA and you ask every guest to move down a room. So N goes to N plus one. So we ask the guests to move to room N plus one. So the first guy goes to room two, the second guy goes to room three, and so on. And since it's an infinite amount of, there are an infinite amount of rooms, we kind of start counting from one. So that way, room one is now vacant and everyone else still has a room. That means we can move the first guy into room one. But what happened here? A supposedly full infinite hotel can still fit more guests. This is the first step to the idea that infinity is a totally different concept and it defines finite rules. Now, let us say, oops, sorry. Now, let us say a bus arrives containing an infinite amount of guests. How would we accommodate an infinite amount of guests? So we have an infinite hotel and an infinite amount of guests, and all the rooms are occupied. But a bus arrives containing an infinite amount of guests. So now we have two different infinities, sort of. So how would we accommodate this bus? You are the manager. You think for a while and then you come up with an idea. We ask the guests this time to move to room 2N. So the first guest would move to room 2, the second would move to room 4, the third guest would move to room 6, and the fourth guest would move to room 8, and so on. So by asking the guests to move to room 2N, that means we have all of the odd numbered rooms that are vacant now. And we know that there is an odd number of, we know that air, we know that there is an infinite number of odd numbers, which means that we can fit this infinite bus. So all of the odd numbered rooms are vacant, and the new guest can be given the odd numbered rooms 2N plus 1. So the infinite bus can go into 1, 3, 5, 7, skipping a number. So what happened here? The hotel's countable infinity just absorbed another countable infinity. What do I mean by countable infinity? There are certain infinities that are, now, first off, we know that infinities can be of different sizes, but there is either countable infinities or uncountable infinities. The amount of rooms in this hotel is considered a countable infinity. The amount of guests in the infinite bus is also considered a countable infinity. So the hotel's countable infinity absorbed another countable infinity. But now, see, this concept is basically the first step towards the idea that there can be different sizes of infinity. This doesn't automatically prove that this can, but there are other steps moving forward, which is a lot more complex, which mathematicians study using infinite sets. But I talked about countable infinity. There are some infinities, like all points on a line, that are strictly larger and won't fit. This is what's called an uncountable infinity. So if I were to tell you to name me all the real numbers in between 0 and 1, you would not be able to do that because there's an uncountably infinite number of real numbers in between 0 and 1. That is considered an uncountable infinity. And I there is a point where Hilbert's Hotel would run out of rooms, and that is when they encounter an uncountable infinity, kind of like the amount of real numbers in between 0 and 1. I find this concept really, really interesting, and there's a YouTube video on Hilbert's Hotel by Veristasium, I believe that's how you pronounce it. It is like 6 minutes long, and I feel like if you guys are, as interested as I am in it, it's just a 6 minute video, and it will really kind of give you a fresh perspective. And I have only talked about half of Hilbert's Hotel, and if you watch that video, you can kind of see what happens when Hilbert's Hotel faces an uncountable infinity. I will, at the end of the session, hopefully be able to paste the link of the YouTube video so you guys can watch it. It's only 6 minutes, and I promise you it is really interesting. So if you guys would take the time out of your day to watch a 6 minute video, it would be very, it's a very interesting concept, and I'm sure you guys will love it as much as I do. Now, we've discussed our phenomena. So let's go to our takeaway. What did we learn from these phenomena? Going back to our original question, where are the limits of mathematical theory? Mathematics is logically perfect, but built on assumptions. If the assumptions hold, then the conclusions follow perfectly. What do I mean by assumptions? Now, assumptions in mathematics is a sort of different concept. Assumptions in mathematics are axioms. An axiom is a statement that is accepted without proof. Let me give you an example. Through 2 points, we know that there is exactly one straight line. That is an axiom. We just accept that statement without proof. Or let me give you another example. Probabilities. Probabilities adding up to 1. That is also an axiom. We just accept that statement without proof. So mathematics does not really prove these axioms from reality. It assumes them and then reasons logically from there. So mathematically speaking, Math is built on assumed axioms, not on empirical evidence. But that is not a flaw. That is sort of how math works. So I also find this very interesting because we know that as long as assumptions hold, that's when the conclusions follow perfectly. But we don't prove these. We just assume them and then we reason logically going forward. So we said that if assumptions hold, then the conclusions follow perfectly. But in the real life, we have constraints, finiteness, uncertainty, and context. Of course, we have discussed this with all the examples that we discussed right now. When assumptions break, results can become misleading or paradoxical. Phenomena like bell curves, gambler's fallacy, paradoxes, and infinity show us that math models reality, but is not reality itself. So, understanding math means knowing when it applies and when it doesn't, knowing when we can model, knowing the concepts that we can model using math and the concepts that we can't model. So, with everything that we've talked about till now, we have illustrated a different limit. All of these examples test the same idea. We know that mathematics is internally perfect. Each step follows logically, but it only really works when assumptions match reality. For example, the bell curve. The bell curve shows how math is incredibly powerful at prediction, but only on average. So these are limits of prediction. There is the gambler's fallacy, which shows us how our intuition kind of misuses probability. These are the limits of human intuition versus probability. The two envelopes problem showed us how a hidden assumption can sort of make math give us an impossible solution and s- a solution impossible to implement in real life. These are the limits of expectation and hidden assumptions. This is sort of it's kind of like a infinite expectation versus a finite reality. We can't model exactly what math tells us to do because of course we can't keep switching envelopes. Hilbert's Hotel. With Hilbert's Hotel, we were shown how infinity completely breaks the rules that we're used to in real life, limits of finite logic when applied to infinity. So, in the real life, and the rules that we are used to are only applicable to finite values because in the real world, we're only used to finite values. Like the rules that we use apply to finite values because infinite infinity does not exist as a concept in the real world. So the limit of mathematical theory isn't that math is wrong, it's that math is abstract while reality is finite, messy, and sort of constrained. Understanding mathematics isn't just about solving equations, it's about knowing when a theory applies, when assumptions what assumptions it relies on, and where it sort of stops representing reality. So mathematics doesn't fail. Our interpretation and application of it does. Now you guys are probably asking me, I did not really explain or clearly answer the question that we originally asked, where is the limit of reality? But the answer is that reality is constrained by physical, empirical, and practical limits, not logical ones. Reality doesn't have formal limits in the way that mathematics does. Its limits come from physical constraints, things like time, space, resources, observation. Mathematics, on the other hand, has precise logical boundaries defined by its assumptions. And the limit isn't in reality itself, it's in how much of reality a mathematical model can capture. When math assumes infinity, perfect randomness, or like unlimited repetition, like in the two envelopes problem, reality can't always follow. And that is where the mismatch happens. So the conclusion is that mathematics doesn't really fail. Our interpretation and our application of it does. We we sort of see math as like I mean, we know that mathematics is theoretically perfect, but it's more about how much math can model that can be mapped back into the real life. Mathematics can model everything, but we can't really apply all of these concepts back into the real life. So I hope that made sense, and I hope you guys, understood and enjoyed these phenomena as much as I did. I remember researching about these for the first time, and I found these so interesting, and I kind of just went down a rabbit hole, and I could not stop researching more and more because uh I mean, I'm a big math nerd and I really find all of this really interesting. So if you guys do as well, then researching phenomena like these is, it's really going to help you, and it's going to you're going to fall down the same rabbit hole that I did and find all of this so fascinating. So if you guys are interested, please do research on this, as I find this really interesting and I'm hoping that you guys will too. So Q&A, you guys can ask me any questions that you have. I'll be more than happy to answer them regarding any of the phenomena that we discussed. All right, I think we have a question.